Okay, that's awkward. I'll just go ahead and move that over me. So it's kind of a weird screencast when you're in a classroom. I'm going to go back to the chat box here. Just move that right there. Okay, so I think I'm recording right now. Here's what I'm going to do for you guys. I'm going to basically just wean down everything and try to condense things into what I think are the main ideas for you guys from now going forward. So this is today, probably realistically, like, I don't know, a week and a half of stuff in pretty much one day, because I'm going to go through the main part of it. And the reason I like to talk about this stuff is because if you take the ACT, the science section is one of the sections that usually has these charts on there. So you don't have to know anything about the science section to do well at the science part, which is kind of weird. But there are charts on here that we will use. Okay. So what chapter is this? I don't know what chapter this is. This is the states of matter and changes of state. So this is kind of, we're just playing the hits. Okay. We're just going through kind of the main idea. So there's going to be a little bit of review. There's going to be times I say, don't worry about this and write this stuff down. So we will start this way. All right. Let me just go. I'm just going to do this real quick. All right. Okay. So real quick, don't have to write these down because I think you probably know what a solid, a liquid, and a gas is. What we're looking at in this section is how these things change state of matter. We're going to look at a couple of changes of state that are a little bit weird. In general, the difference between a solid, liquid, and a gas. For us right now, we're just going to talk about how close our particles are to each other. So a solid is something that has a definite shape and a definite volume. This means that, like I said, I'm not writing this stuff out. If you guys want to fill in the blanks, or that's fine. Definite shape and definite volume. So when you have a solid, the particles are locked into place. A liquid has an indefinite shape, but a definite volume. So that is to say that the shape of a liquid, it just takes the shape of whatever its container is, but the volume does not change. So if like you try to compress a volume, I can't squeeze the water molecules closer to each other. All right. And then we have a gas, which has an indefinite shape and an indefinite volume. So if we're talking about a syringe, which I'm going to use the syringe today for the liquid, but a syringe, I don't know if you guys can see this. We have 55 cc's of gas in here. And if we compress it, we can squeeze it into about 10 cc's comfortably. Okay. What we're going to look at is how these things interact and how they change state. That's going to be our goal in this little section. Like I said, I'm going to try to just play the hits here. I'm not going to talk too much about freezing and melting because I feel like you know what those are all about. The big one for us is to kind of identify two different types of what we call vaporization. Vaporization is the fancy term for when you go from a liquid to a gas. A liquid to a gas is vaporization. Now you might say that, well, isn't that like boiling or evaporation? These are forms of vaporization that I'm going to talk about. All right. So the first type of vaporization is the type that occurs at the surface of a liquid. It's called evaporation. We're going to probably spend more time talking about boiling, but I do want to talk about evaporation real quickly. Evaporation, the idea behind it is that only molecules that have a certain amount of energy can escape the liquid phase. So the idea scientists will talk about here is that all these little particles in here are moving at kind of their own little speed. Sometimes they can gather up enough speed to go ahead and peace out. So they can go ahead and escape this liquid phase. And if you leave the lid off of a beaker full of water and we just let it sit back there, we come back in like August, there's going to be no water left over because it's all going to evaporate. Okay. This is kind of a duh. Evaporation occurs better when things are hotter. So like hot water will evaporate quicker than cold water just because those particles have a little bit more of that energy. Or if you dump water on a hot surface, it's going to evaporate way quicker. Okay. This is a cooling process. So evaporation, something that we may get to later, I don't know, is a cooling process because it takes energy away from the system. This is why we sweat. When you throw water on your skin, you put water on your skin, and that stuff evaporates, it naturally cools your body. So sweating is very important for us, even though it's kind of gross at times. It's a very important thing because it's the way we can cool ourselves, okay? So evaporation is the first type of vaporization. The second type, you have to kind of understand how vapor pressure works. And like I said, I'm trying to go through some terms and some new things for you guys to kind of like condense it. So vapor pressure, if you understand what vapor pressure is, you'll understand why boiling, our next type, is so dependent on it, okay? So vapor pressure and the idea behind vapor pressure. It sounds kind of stupid, but vapor pressure is the pressure that a vapor exerts when it tries to evaporate. So like if you have two different liquids, let's just say we have some water here, all right? And then we have something that really evaporates easily, gasoline here, okay? Gasoline really vaporizes very easily. So what happens is that as these guys are vaporizing and as they're evaporating, gasoline does it easier, okay? And it has to do with the stickiness of the gasoline molecules and how they'd rather just go be the gaseous state. But basically the idea behind vapor pressure is that gasoline would have more of a vapor pressure than water, assuming they're at the same temperature. So you have to kind of understand that vapor pressure is this pressure of a vapor pushing up and leaving. Now, if I put a lid on this gasoline beaker and I put a lid on the water beaker, what's going to happen is that this is going to become much more pressurized because there's more vapor particles in there, okay? You guys might experience this if you ever like go to your shed when you're going to mow the lawn in the summer or whatever, and you open up the gas tank and you usually hear kind of this big pressure release because gasoline vaporizes so much easier. Things that have a high vapor pressure will evaporate easier. In a closed system, these things tend to balance out. Today, we're going to talk about closed systems and what happens. We call this equilibrium, but the idea is this. If I put a lid on a beaker of water, it will get to the point where for every guy that is evaporating, there's going to be something that's condensing. So it looks like to us that nothing is happening, but it reaches this state of equilibrium that we'll look at in a little bit, okay? If at any point you need me to slow down, I will post these slides. I will post this, this video online as well. So like if you want me to slow down, just unmute yourself and holler at me. Or if you have any questions, let you go, because right now it feels like I'm talking to myself, but that's okay, right? Okay, so the second type, and this is why we need to talk about vapor pressure, is boiling, okay? And boiling.
Can you go back just for 1 second?
Yeah, there you go.
I'm sorry.
That's how you do it, right there, okay? So we're going to talk a little bit about closed systems and equilibrium when we get to boiling. I'm going to, I don't even know if this will work very easily for you guys, if you'll be able to see it. So hopefully I have a demonstration that's kind of cool that is a little bit weird when we think of boiling. Okay?
Okay, I'm cool now. Thank you.
You're cool now? Okay, sweet. Yep. All right, so second type of vaporization is called boiling. And this is going to be the one that we spend more time on. The idea behind boiling and the whole idea where what means that you're boiling. Boiling is a stage of vaporization where not just the things at the surface are leaving, but everything throughout the liquid can vaporize. So like you guys know that something is boiling because you see bubbles. You see these bubbles that are vaporizing usually at the source of the heat, which is at the bottom. Bubbles are less dense because they're gaseous, so they go ahead and they leave, okay? And that's when you guys know when to throw in the mac and cheese and all that stuff, all right? And throw the macaroni noodles. So boiling is the point at which particles throughout can vaporize. And this is the key for us today, and this is kind of the weird thing. boiling is dependent a lot of times on pressure. And all phase changes, even though we don't think of them as being so, are dependent on pressure. So you can get something to boil when the vapor pressure of the liquid is equal to the atmospheric pressure pushing down. And it's equal or greater than, okay? So what the heck does that mean? Well, normally when you want to boil something, you have to heat it up. When you heat up, we'll just use water as an example. When you heat up water, you get more vapor particles. They want to leave, okay? But the thing that keeps this as a liquid is this atmospheric pressure. Atmospheric pressure is fancy talk for air pressure. So the air in the room is basically shoving down the liquid saying, stay liquid, stay liquid. What are you doing? Why are you bubbling? What happens is that as we add more and more heat, we get to the point where these guys can escape. And when they escape, that's when you reach the boiling point. So here's my point. We have been taught in our classes forever that water will boil at 100 degrees Celsius or 212 Fahrenheit. Okay, well, that is true. It totally does boil at that temperature, but it can also boil at different temperatures based on changing air pressure, because air pressure is different everywhere. So I'm going to show you guys a demonstration on boiling water. And anything on this slide, you don't have to write down, okay? Don't even worry about this. It just has some different boiling points depending on where you're located, okay? So the question is boiling water always hot? Well, boiling water doesn't always have to be hot because, and this is the key for today, the boiling point is dependent on how warm and what's the pressure. So it's going to sound dumb, but water doesn't boil at the same temperature in Denver as it does here. And it doesn't boil at the same temperature here as it does in San Diego, because the air pressures are very different based on altitude and elevation, okay? So what we're going to do today is we're going to change the atmospheric pressure on the liquid, okay? And the way we're going to do that is we're going to use a syringe. So a syringe is an easy system to increase the pressure, or the way we decrease the pressure is we close the system and we pull the plunger. Now, when I let go, air pressure is going to, from out here, because it's higher, is going to push the plunger in, okay? So when you guys learn that water boils at 100 degrees Celsius, and I'm going to use Celsius because this is a science class and I'm a nerd like that. You guys learned 100 degrees Celsius because you don't want to learn a zillion different boiling points, okay? We don't want to worry about pressure changing. So when we say that it boils at about 100 degrees Celsius, that's the pressure that you experience most of the time at sea level. So water will boil at 100 degrees Celsius. In Sydney, I don't know, I must have done this earlier this year where when I was making this slide, the air pressure was at a point where in Sydney it boiled at 95.8 degrees Celsius, okay? Why does it boil at a lower temperature here? It boils at a lower temperature because in Sydney, we're above 4,200 feet above sea level, which means that there is not as much air pushing down on water. If you guys have went into the mountains and you've ran around for more than 2 minutes, you realize, oh my God, I cannot breathe. You can't breathe because there's less oxygen up there. There's less air pressure, less oxygen up there, okay? If you go to Denver, it's about 95 degrees Celsius. Denver is about 5,000 feet above sea level, okay? Today's demonstration, Mount Everest. If you went to the top of Mount Everest and you tried to boil water, they would boil at 70 degrees Celsius, once again, because as you go higher and higher in altitude, there's less air pressure pushing down in you, okay? If you have a pressure cooker, okay, old school pressure cooker, it's about 110 degrees Celsius, or an Instant Pot, which gets super duper hot, okay? Here's what I'm gonna do. I have some water over here that is about 68 degrees Celsius, okay? And I don't know if you'll be able to see this or not, so you'll just have to bear with me. Okay, so what does 68 degrees Celsius feels like? It feels pretty warm, all right? Now, what I'm going to do is I'm going to pull the plunger and I'm going to decrease the pressure inside of here, right? And I don't know if you guys can see this or not. Ugh. Okay, so I don't know if you guys can see that, but it's boiling, and I can get it to stop boiling very quickly by increasing the pressure, okay? I'll do that again. Like I said, it's not ideal. It'd be easier if I could walk around the classroom. You guys were here, all right? So I'll just go ahead and pull the plunger again. You guys can see that boiling. The water is boiling. It's not increasing the temperature. It's increasing the pressure. Or sorry, decreasing the pressure. So can you boil water that's not hot? Yeah, you just got to take away the pressure associated with it. And here's the idea. In order to cook your noodles, you want the temperature to be higher. So it wouldn't make much sense, or it would take you forever to cook your noodles in that gross syringe there, because we're cooking at 65 degrees Celsius, okay? So the thing about boiling temperatures also is that once it starts boiling, it stabilizes. It stays that temperature. That's going to be something that we look at down the road, okay? So why do pressure cookers and Instant Pots cook your food so much quicker? Because it creates a pressurized system where the temperature inside is cooking at a higher temperature. Maybe the water doesn't boil at 100 degrees. Maybe it boils at 110 or 115 or 120. If you have water that's at 120 degrees, it's going to cook your stuff a lot faster. So even though water is going to boil faster on Mount Everest, it's going to take forever to cook because once it's boiling, it stays that temperature. Okay? All right, I'm going to push pause. Does anybody have any questions about that concept? All right, so here's the deal. When you have when you are boiling something, we don't want to memorize 755 different boiling points based on where you're at. Also, I will tell you right now, the boiling point in Sydney changes because air pressure changes. So what you guys learned when you were kids about freezing points and boiling points of water were things called the normal boiling point. The normal boiling point is going to be what we use in all of our calculations. And it's the boiling point of a substance at a standard pressure. So there are different ways to measure pressure of gases. If you were to measure the pressure of the gases in your tires, you would use PSI, pounds per square inch. But we don't use those. We use these values here. We use something called an atmosphere or something called a kilopascal. Okay, these are atmospheres. ATM stands for atmospheres. kPa stands for kilopascals. In our next section, we'll deal a lot more with pressures. But the idea is this. Water has a boiling point of 100 degrees Celsius at 1 atmosphere or 101.3 kPa. Okay, so now we're coupling a boiling point with a pressure. So the normal boiling point, water can boil at 70, but it's just that it's not going to be at that pressure. So pressure is very important in our determining what the state of matter is going to be. Okay, so I'm going to show you guys. I'll finish this little discussion with a chart or a diagram that kind of puts all this stuff together in terms of what's your pressure, what's your temperature. All right. So what's the normal freezing point of water? Water can freeze at lots of different temperatures because pressure is important. Water's normal freezing point is 0 degrees Celsius. Okay. So we say that water has a boiling point of 100 degrees Celsius at 1 atmosphere. Okay. Now, with all that being said, I'm basically telling you all this because I want you to be able to read this chart that I'm going to show you. You see it pop up a lot of the times on ACTs, which we would be taking the ACT if it was a normal situation here. Okay. So changes of state. I don't know why that slide looks like that. So I'm just going to rewrite this real quick. Okay. So we have solid. So let's see here. Bear with me. Okay. I'm just going to write some arrows there. I don't know why those didn't come off. Didn't like that format. Okay. So this stands for solid, liquid, gas. Okay. So solid, liquid, gas. if you were going from a solid to a liquid, we call this process melting. Okay, we call that process melting. You melt it into a liquid. You go from a liquid to a solid. We call that process freezing. Okay. You guys are like, no kidding. We got that, right? If you're going from, make sure my arrows are in the same direction, liquid to a gas, you guys have today learned that that is called vaporization. Okay? If you're going from a gas to a liquid, we call that condensation. Okay? Now, here's the weird one. There is the ability to go from a solid to a gas and skip the liquid phase. This is what dry ice does. I'll show you why it happens today. Okay? A solid to a gas is called sublimation. Okay? Sublimation. So dry ice is called dry ice because it doesn't melt. It goes straight from a solid to a gas and it skips the whole liquid phase, which means that it's dry. So you don't have like soggy stuff when they, and this is how they transfer food or they pack food. If like you ordered something from Omaha Steaks, they're probably going to send it with some dry ice. Okay. The opposite process here, I'm just going to write it up here. I think you guys can see this. So this opposite process is called deposition. Jeez, that's terrible. Deposition. Okay. It's going from a gas to a solid. This is how frost forms on your windshield. It doesn't freeze in little droplets. It looks like pretty little snowflakes on your windshield. It's very annoying. Okay. So those are the changes of state that we're going to look at. And I'm going to show you guys how this all kind of works out on a chart. Okay. So, oh, perfect. All right. I don't want to go very long on these things. You can imagine. Very boring. Very boring. Okay. So the way that we put together temperature and pressure on a diagram is we use this thing called a phase diagram. I'm going to go through some of the guts of a phase diagram, and then I'm going to draw just kind of a general one on the board and show you the main areas and the things that we look for in a phase diagram. So a phase diagram is a diagram that shows you not only the temperature that you have to be a certain state of matter, but it shows you the pressure as well. Okay. So what we are looking for are points when you reach what's called equilibrium. Equilibrium is when you are melting and freezing at the same rate, or boiling, vaporizing, or condensing at the same rate. So it's in a very closed system, and it has to be a very specific temperature and pressure for this to happen. Okay. Equilibrium is when both these things form at the same rate. So here's a really dumb, easy equilibrium for you. If you have a bottle of water, okay? So if you have a bottle of water, okay, there's my bottle or whatever, and I have the lid closed, right? So that's my hydro flask here. Now, this water inside, as it heats up over time, it might evaporate a little bit, okay? So maybe the water level goes from here to there. Okay, but it will reach this point of equilibrium where for every one particle that's vaporizing, one particle is being condensed. So it looks like to us nothing's happening, even though there's stuff happening. It's happening at the same rate. The lines on our chart today are going to represent equilibrium. So what a phase diagram does is it shows you the relationship between all phases on a graph. Okay. Shows you the phases, all three. The lines in the graph are the pressures and temperatures where the two phases are in equilibrium. So where you see these lines today, you can think of, oh, that's where it's melting or freezing. That's the way we're going to think of it today. Oh, that's where it is either vaporizing or condensing. Kind of depends on if you're adding energy or taking energy away. Okay, so phase diagram. I'm going to draw a general one on the board. I'm going to label some areas here, and that will be our life. Also, I'll show you a couple of the points that are very unique and weird, and we'll talk about why we never see a puddle of carbon dioxide, why dry ice is a thing. Okay, that's what we'll finish with. So phase diagram. A phase diagram is a diagram that's an XY axis, and it has on the X-axis temperature. Okay, today our temperature is going to be in Celsius degrees. I'm making this up, guys. This is just kind of a general chart here. So I don't know. Let's just say zeros there and 10s there and 20s there. It doesn't matter. Okay, we're just making stuff up. And then on this side is going to be the pressure. And today we're just going to say that the pressure is going to be in ATM. And you're like, what the heck's an ATM? That's called an atmosphere. Don't worry about it. We'll get to it down the road. Let's just say that this is the, I don't know, this is 0.5, and this is 1, and this is 1.5, and this is 2, something like that. Doesn't really matter, okay? So phase diagram is going to have the general shape, and I'm just kind of making this up, so don't stress, like, why is it like that? It just kind of is, okay? Okay, there's 3 main sections of a phase diagram, and they all kind of have, sometimes this line is slanted back this way for like water and things like that. Don't worry about why right now, but these are the 3 sections. This section is where you'd find a solid. So this is the temperature and pressure where you would expect a solid to exist. This area right here is the liquid spot. So to be a liquid, like at 20 degrees and 1.5 ATM, I would be a liquid. And then down here, this is the gaseous spot. So anything in this temperature and pressure range is a gas, okay? Anything in a temperature and pressure range is a gas. So easy example would be like, hey, what state of matter would you be if I said you were a solid at 0, or said if you were at 0 degrees Celsius and 2 atmospheres? 0, 2, boom, you're a solid, okay? That's how you read a phase diagram, right? Now, on a phase diagram, this is where those little processes are occurring. So this, we'll just do the easy ones. If I'm going from a solid to a liquid, that's where melting occurs. If I'm going from a liquid to a solid, that's where freezing occurs. If I'm going from a liquid to a gas, that's where vaporization occurs. Gas to a liquid, that's where condensation occurs. And then solid to the gaseous phase, that's where sublimation occurs. That's where deposition occurs, okay? So those are kind of the areas where you can expect those changes of state, okay? A couple of locations on here that you need to be familiar with, right? So I'm going to go ahead and color this guy in green, right there. What is that thing called, okay? That is a very special point on a phase diagram where you've got everything occurring. You've got freezing, melting, vaporizing, condensation, sublimation, deposition. Everything is occurring there. That is called, I don't know if you guys can see this. It's called the triple point, okay? This is where everything's in equilibrium, right there. That's a very special spot. How many triple points are there for a given phase? 1 triple point, okay? So that's called the triple point. Now, if we said, hey, what's the boiling point of this stuff? Well, the boiling point could be anything along this line right here, okay? Anything along this line is the boiling point. So typically what we say is, I want to know the normal boiling point. The normal boiling point is the boiling point along this 1 atmosphere line. So the boiling point that I would care about would be that point right there. Okay, and that looks like it's pretty close to 20. So at 1 atmosphere of pressure, that is the point at which we'd expect it to boil at 20 degrees, or it looks like about 21, okay? That's a point where you would expect freezing or melting to occur. So the normal melting point would be about 10 degrees. That's how we say, that's how we do that, okay? So those are phase diagrams. Those are the points that I want you to know. I'm not even going to talk about the critical point right now, okay? That looks like a freaking mess as I look up there. Hopefully yours is a little bit more organized than mine. But here's my point. I'm going to erase this mess. If you don't mean to erase it, unmute yourself and say, don't erase it yet. 4, 3, 2, 1. Okay, so here's why you never see a puddle of carbon dioxide. Real quickly, you don't have to write this down. I just want to show you guys what I'm talking about. Okay, so carbon dioxide. Solid, liquid, gas. All right? So this is where we live. We live at this pressure, about 1 atmosphere, right here. Okay? We don't live up here in this pressure. This pressure up here is way too high for us. To get a liquid phase of carbon dioxide, you would have to increase the pressure 5 times the amount of pressure that's in your room right now. That would be very uncomfortable. So since we live at this area right here, that's why we don't see a puddle of carbon dioxide ever. We see the dry ice go from a solid straight to a gas under sublimation, okay? And once again, why? Because this pressure is way too high. To get it liquid, you have to condense it and you have to compress it, and it's a mess, okay? So that's phase diagrams. Does anybody have any questions? All right, I will post the slides on here. There will probably be some terms and some things that, yeah, triple point, critical point. I mean, I'm not really going to worry about that. Make sure you know what the triple point is. There's carbon dioxide's thing, okay? That's all I'm going to say about that stuff, all right? So I'm done with that business. Like I said, I'm sorry I talked so much. That was like 30 minutes of that business. I would like to give you guys some time to ask questions about the take-home quiz. I don't even know when I said that was due. Do you guys know when it's due? Is it due today? Is it due tomorrow? Most things are going to be due on Tuesday nights, I think, going forward. All right. Tomorrow, thank you, Gage. Okay, so what questions do you have about the take-home quiz? I will hang out here, or I'll also answer any questions, or if you just want to hang out and chat, that's cool too. I don't really care. All right, we're going to talk to each other, work on it together in this format. Look at that, 17 whole people here. Good job, guys. It's pretty good. Okay. All right, so I'm going to hang out. If you guys need anything, just holler at me. I won't shut this down for a little bit. Okay? And if you want to bail, there's a chat right there. Let's see what it says. Okay, thank you, Carly. It is due at 8 a.m. tomorrow. So I will probably change the due date time on that, not so you guys can procrastinate more. I think, I'm not sure, but I think we had a staff meeting the other day, and a couple of things are going to happen. I think our due dates are all going to be like Tuesday night at 11:59 p.m. or something along those lines. I think that might happen. If it doesn't for your other classes, you know, just pay attention to that. But I think that might happen. Also, the amount of assignments you get will be more standardized. Like I'm only given 2 a week. And I think that's going to be the case going forward, is that your assignment values will be in the 1 to 2 range, depending on if your class is a core class or if it is an elective course or whatever. Okay. So anybody have any questions about the take-home quiz? Now's the time. Or tomorrow, like I said, check Google Classroom. I will post a announcement on Classroom when my office hours will be. I'll send you guys an invite to it. I'm probably going to invite all my classes, so I might have some Chem 2 and some physics people in there. I don't really care. It's like coming to my room 8th hour, right? So that's that. Okay. People are bailing. We out. Okay, I'm going to stop recording this. I'm just going to stay on, but I'm going to stop